Welcome! In this session, we'll explore problem number 501, find mode in binary search tree. This problem involves identifying the most frequently occurring elements in a BST. We'll discuss an effective approach to solve it, its time and space complexity, and key takeaways. Let's dive in. In this problem, we are tasked with finding the mode or modes in a binary search tree, also known as a BST. The mode is defined as the value or values that appear most frequently in the tree. If there are multiple modes, we can return them in any order. Now, let's recall the properties of a BST. For any node in the tree, all the values in its left subtree are less than or equal to the node's value, and all the values in its right subtree are greater than or equal to the node's value. Both the left and right subtrees must also follow the same BST structure. The input will be the root of the BST, which is given as a tree node object, and the output will be a list of integers representing the mode or modes in the tree. Let's look at some examples to better understand the problem. In the first example, the input BST is represented as 1, null, 2, 2. If we visualize the tree structure, the root node is 1, with a right child of 2, and that node has its own left child, which is also 2. Here, the value 2 occurs twice, while the value 1 occurs only once. Since 2 appears more frequently than any other value, it is the mode of the tree. Therefore, the output is 2. In the second example, the input BST is 0, which means the tree consists of only a single node with the value 0. Since there is only one value in the tree, it is the most frequent value by default. Thus, the mode is 0, and that is our output. In the third example, the input BST is 3, 1, 4, 1, 2, and the tree is structured as follows. The root node is 3, with 1 as its left child and 4 as its right child. The left child of 1 is null, but it has a right child with the value 2, which in turn has a left child that is also 1. Observing this tree, we can see that the value 1 appears twice, which is more than any other value in the tree. Therefore, the mode is 1, and that is the output. Now, let's review some constraints and edge cases for this problem. First, the number of nodes in the tree can range from 1 to 10,000. Each node's value will lie between negative 100,000 and positive 100,000, and the tree is guaranteed to be a valid BST. For edge cases, consider a single node tree. In such cases, the mode is simply the value of that single node. If all nodes in the tree have the same value, that value is the mode. When the tree has multiple modes, all of them should be included in the output, but their order does not matter. Lastly, given the possibility of very large trees, it's important to ensure that our solution is efficient and can handle these cases within the problem's constraints. When approaching this problem, one of the first methods we can consider is a brute force approach using a hash map. The intuition here is straightforward. We traverse the binary search tree and count the frequency of each value. To do this, we can store value frequency pairs in a hash map, which allows us to keep track of how many times each value appears. The process involves three main steps. First, we perform an in-order traversal of the BST to collect all the node values into a list. Then, we iterate through this list and use the hash map to count how often each value occurs. Finally, we find the maximum frequency and extract all the values that match this frequency to identify the modes. The time complexity of this approach is O(n), which includes the traversal and counting steps, but it comes with a space complexity of O(n), due to the hash map. While this method is intuitive and simple to implement, its trade-off lies in the additional memory requirement, which isn't optimal for a tree structure that we could explore more efficiently. Now, a more optimized approach leverages the properties of an in-order traversal with constant additional space. The key intuition here is that an in-order traversal of a BST processes elements in sorted order. This allows us to count the frequency of values on the fly, eliminating the need for extra storage. The steps are as follows. As we traverse the tree, we keep track of the previous value we visited, its frequency, and the maximum frequency observed so far. If the current value matches the previous value, we simply increment the count, otherwise, we reset the count to 1 for the new value. Whenever the count exceeds the maximum frequency, we update the modes. By the end of the traversal, we'll have identified the modes without needing to store all node values. This approach runs in O(n) time, like the brute force method, but its critical advantage is the O(1) additional space requirement, excluding the recursion stack. However, this method does come with trade-offs. It's harder to implement because it requires careful handling of transitions between values and edge cases, such as an empty tree. Still, its efficiency makes it a strong candidate for solving this problem. The optimized approach is ultimately the chosen strategy for this problem due to its space efficiency and its ability to directly utilize the properties of a binary search tree. While the hashmap method is simple and intuitive, it consumes memory proportional to the number of unique values in the tree, which makes it less optimal for memory-constrained scenarios. The optimized approach, on the other hand, takes advantage of the in-order traversal's natural ordering to count frequencies without extra storage. This method relies on tracking only the previous value and its frequency, which eliminates the need for storing all the node values. The aha moment here lies in recognizing that the tree structure itself provides all the necessary information in sorted order, simplifying the process. For larger BSTs, this space-saving advantage becomes crucial. Though slightly more complex to implement due to its reliance on traversal logic and edge case handling, the optimized approach strikes the right balance between time efficiency and minimal memory usage. This makes it the best solution for efficiently finding the mode in a binary search tree. In this problem, our goal is to identify the mode or modes in a binary search tree. The mode refers to the value or values that occur most frequently in the tree. A binary search tree, or BST, follows a couple of key properties. In the left subtree of any node, the values are always less than the node's value, and in the right subtree, the values are always greater. To solve this, we'll start with a brute force approach that uses a hashmap to store the frequency of each node value. First, we initialize our data structures, specifically a hashmap where the keys are the node values and the values represent their frequencies. Then, we traverse the BST using an in-order traversal, which visits nodes in sorted order. As we visit each node, we update the hashmap. If the value already exists, we increment its frequency, and if it's new, we add it to the hashmap with a frequency of 1. This sets the foundation for identifying the mode. After completing the traversal and populating our hashmap with value frequencies, the next step is to find the maximum frequency. To do this, we iterate through the hashmap and track the highest frequency observed. Once we know this maximum frequency, we can collect all the values from the hashmap that have this frequency. These values represent the mode or modes of the BST. Finally, we return these modes as a list or an array, which becomes the output of our algorithm. This straightforward approach ensures that we capture the most frequent values in the tree efficiently, completing the process of finding the mode. This solution leverages several important insights. First, the in-order traversal is key to working with BSTs, as it visits nodes in sorted order, which allows us to maintain clarity and verify correctness. While this ordering isn't strictly necessary for the brute force approach, it aligns well with the BST structure. The hashmap is another essential component, allowing us to count frequencies efficiently with an average time complexity of O(1) for insertions and lookups. Overall, the algorithm is efficient. We traverse the tree once, which takes O(n) time, and then iterate through the hashmap to find the maximum frequency and collect the modes, which takes O(k), where k is the number of unique values. This ensures that our solution is both straightforward and performant. The core data structures we rely on are the hashmap for frequency counting and a list or array to store the final modes for output. The key operations in this algorithm include the in-order traversal, which ensures nodes are visited in sorted order and has a time complexity of O(n). Next, we perform hashmap updates, where we either insert new values or update the frequency of existing ones, both of which have an average time complexity of O(1). Finding the maximum frequency involves a linear scan of the hashmap, which is O(k), and collecting the modes requires another linear scan of the hashmap, also O(k). Beyond these operations, we must handle certain edge cases. For example, if all nodes have the same value, the hashmap will only have one key, and that value will be the mode. For a tree with a single node, the single value is the mode. If all values are unique, each value will have a frequency of 1, meaning all of them are modes. In the case of an empty tree, there are no nodes, so the output should simply be an empty list. Although the brute force approach is simple and effective, there are opportunities for optimization. For instance, by performing a two-pass in-order traversal, we can compute the modes in O(n) time and O(1) space, avoiding the need for a hash map altogether. In terms of complexity, the time complexity of the current approach is O(n), where n is the number of nodes in the tree. This includes O(n) for the in-order traversal and O(k) for iterating through the hash map, where k is the number of unique values. The space complexity is O(k), as we store all unique values in the hash map. To illustrate the process, let's consider an example where the BST contains the values 2, 1, 2, 3, 2. During the in-order traversal, we visit the nodes in the sequence 1, 2, 2, 2, 3. The hash map updates as follows: first 1, 1, then 1, 1, 2, 1, then 1, 1, 2, 2, then 1, 1, 2, 3, and finally 1, 1, 2, 3, 3, 1. The maximum frequency is 3. Once we have the maximum frequency, which is 3, the next step is to collect all the keys from the hash map that have this frequency. In this example, the value 2 has a frequency of 3, so the modes are 2. This list becomes our output. By following these steps, we've successfully identified the mode of the BST using the brute force approach. This method, while straightforward, highlights key concepts such as in-order traversal, efficient frequency counting with a hash map, and handling edge cases effectively. The example demonstrates how the algorithm processes the BST step by step, ensuring clarity and correctness in the result. Here, we start by importing the defaulted class from the collections module, which helps us create a dictionary that initializes values to a default type, in this case, integers starting at 0. Then, we define our solution class and the findMode method, which takes the root of the binary search tree as input. If the root is null, meaning the tree is empty, we simply return an empty list since there are no nodes to process. To count the frequency of each value in the tree, we use a default dict called frequency_map. We then define a helper function, in-order_traversal, which is responsible for performing an in-order traversal of the binary search tree. This traversal lets us process nodes in ascending order of their values, as is characteristic of binary search trees. The function is recursive, so it first checks if the current node is null and exits if so. Otherwise, it recursively visits the left subtree, increments the frequency count of the current node's value in frequency_map, and then proceeds to the right subtree. By the end of this traversal, frequency_map will contain the frequency count of all node values in the tree. Once the in-order traversal is complete, we calculate the maximum frequency by taking the highest value from frequency_map.values. This represents the most frequently occurring value or values in the tree. Using this maximum frequency, we then construct a list of all keys in frequency_map whose counts match this maximum. These keys represent the modes of the tree, and we store them in the modes list. Finally, we return this list as the result. This approach ensures that we efficiently find all modes in the binary search tree while maintaining a clean and readable structure in our code. To solve the problem of finding the mode in a binary search tree, we start by importing the necessary utilities and defining the solution class. Within this class, we have the findMode method, which is the main function. The first step is to check if the root of the tree is null. If it is, we simply return an empty array since there are no values to process. Next, we use a hash map to store the frequencies of each value in the tree. This map will help us count how many times each unique value appears. To populate this frequency map, we perform an in-order traversal of the tree using a helper method called in-order traversal. Once the traversal is complete, we determine the maximum frequency by finding the highest value in the map. After identifying the maximum frequency, we create a list called modeslist to collect all the values that occur with this maximum frequency. By iterating through the map entries, we add keys to this list if their frequency matches the maximum frequency. Finally, we prepare to convert this list of modes into an array for the result. After collecting the modes into the list, we proceed to convert modeslist into an integer array. This is done by iterating through the list and assigning each value to the corresponding index in the array. Once the array is fully populated, we return it as the result of the findMode method. Now, let's take a look at the in-order traversal method, which is the helper function used to populate the frequency map. This method takes a tree node and the frequency map as parameters. It first checks if the current node is null, and if so, it simply returns to avoid further processing. Otherwise, it recursively traverses the left subtree, processes the current node by updating its value in the frequency map, and then recursively traverses the right subtree. This ensures that the tree is visited in order sequence, which is crucial for maintaining the structure of a binary search tree. Finally, we define the treenode class, which represents the nodes in the binary search tree. Each node has three attributes: val, which holds the value of the node, and left and right, which are references to the left and right child nodes. The class provides two constructors, one that initializes an empty node and another that allows initialization of a node with a specific value. Additionally, there's a third constructor that sets both the value and the left and right child nodes. This structure allows us to create and manipulate binary search trees efficiently, which is essential for solving the problem of finding the mode in the tree. To solve the problem of finding the mode in a binary search tree, we start with an example where the BST has unique elements. The tree is structured with 2 as the root, and 1 and 3 as its left and right children, respectively. First, we initialize an empty frequency map, frequency_map, to keep track of how many times each value appears in the tree. Then, we begin an in-order traversal, which processes the left subtree, then the root, and finally the right subtree. Starting with the left subtree, we visit node 1, record its value in the frequency map, and increment its count. At this point, frequency_map becomes 1, 1. We then return to the root node 2 and update the frequency map to include its value, resulting in frequency_map equals 1, 1, 2, 1. Finally, we move to the right subtree, visit node 3, and update the frequency map again, making it 1, 1, 2, 1, 3, 1. After completing the traversal, the frequency map contains all the values in the BST along with their respective counts. To find the mode, we determine the maximum frequency in the map. In this example, the maximum frequency is 1, which means all values occur only once. We then collect all the keys with this maximum frequency, resulting in the modes 1, 2, 3. Moving to the second example, the BST now has a mode because the root value 2 appears twice. The tree has 2 as the root, with 1 as its left child and another 2 as its right child. We start with an empty frequency map and perform an in-order traversal, beginning at the left subtree. Visiting node 1 in the left subtree, we add its value to the frequency map, making frequency_map equals 1, 1. Returning to the root node 2, we increment its count in the map, updating frequency_map to 1, 1, 2, 1. Next, we move to the right subtree and visit the second occurrence of node 2. This increments the count of 2 in the frequency map, resulting in frequency_map equals 1, 1, 2, 2. With the traversal complete, we calculate the maximum frequency, which is now 2. Collecting the keys with this frequency gives us the mode 2. For the third example, the BST is structured such that all nodes have the same value of 1, making this a straightforward case. Here, the BST has 1 as the root, with both its left and right children also being 1. Starting with an empty frequency map, we begin the in-order traversal. In the left subtree, we visit the first node with value 1 and record it in the frequency map as 1, 1. Returning to the root, we increment the count of 1, updating frequency_map to 1, 2. Finally, we proceed to the right subtree, visit the last node with value 1, and update the map again, resulting in frequency_map equals 1, 3. The maximum frequency is 3, as all nodes share the same value. Collecting the keys with this frequency gives us the mode 1. This demonstrates how the algorithm efficiently handles different cases, from unique elements to repeated values in the BST. To determine the time complexity of the solution, we break it into 3 main components. First, the in-order traversal of the binary search tree visits each node exactly once. During this traversal, we update the frequency map for each node value in constant time. If the tree has n nodes, this step takes n time. Next, we find the maximum frequency by iterating through the values in the frequency map. Here, the number of distinct values in the tree is denoted as k, so this operation requires k time. Finally, we collect the modes by iterating over the frequency map again to extract keys with the maximum frequency, which also takes k time. These steps together form the foundation of our time complexity analysis. When we combine all the components, the total time complexity is O, n plus k, where n is the number of nodes and k is the number of distinct values in the binary search tree. In the worst case, where all nodes have unique values, k equals n, and the time complexity simplifies to O, n. Now, looking at the space complexity, we need to account for both the recursion stack and the frequency map. The recursion stack depth depends on the height of the tree, which is O log n, for a balanced tree, and O, n, for a completely skewed tree. The frequency map, which stores the count of each distinct value, uses O, k, space. In the worst case, where all values are unique, this becomes O, n. We also need to consider the space used by the output list, which stores the modes of the tree. If there are k distinct modes, the list will require O, k, space. Combining all these factors, the total space complexity is determined by the larger of the recursion stack and the size of the frequency map. In the worst case, where the tree is skewed, or all values are unique, the space complexity is O, n. In the best case, for a balanced tree with fewer distinct values, the space complexity is O log n plus k. These are the key aspects that influence the space requirements of the algorithm. When comparing this solution to a naive approach, the difference in efficiency becomes clear. A brute force method would involve traversing the tree multiple times, once for each unique value, to count occurrences. This would result in a time complexity of O, n asterisk k, which is far less efficient than the current solution's O, n plus k. The space complexity remains similar at O, n, since both approaches would need to store the tree's data. The current solution, however, optimizes performance by leveraging a single in-order traversal and a frequency map for constant time updates. In summary, the algorithm achieves a time complexity of O, n plus k, with a worst-case scenario of O, n, and a space complexity of O, n, in the worst case, or O, log n plus k, in the best case. This makes it both time and space efficient compared to the naive approach, striking a balance between simplicity and optimization. When solving this problem, there are a few common mistakes to watch out for. First, many people confuse the properties of a binary search tree with those of a general binary tree. Remember, a BST has a specific structure where the left child is less than the root, and the root is less than the right child. Generic binary tree traversal methods often overlook the fact that an in-order traversal of a BST yields a sorted sequence, which is a key insight for solving this problem efficiently. Another mistake is performing inefficient traversal or redundant computations. For example, repeatedly traversing the tree to count values or find the maximum frequency adds unnecessary time complexity. Instead, aim to collect all necessary information, such as value frequencies, in a single pass through the tree. Lastly, edge cases are often mismanaged. Scenarios like an empty tree, a tree with just one node, or trees containing duplicate values can easily lead to runtime errors if not handled properly. To avoid this, always start by explicitly checking for these cases in your solution and ensure your test cases cover these situations thoroughly. In addition to these mistakes, improper use of recursion is another challenge to be mindful of. Recursive solutions, while elegant, can fail for deeply unbalanced trees due to stack overflow errors. To address this, consider using an iterative approach with an explicit stack. Alternatively, if the programming language supports it, ensure your recursion is tail-optimized to mitigate stack usage. Another common issue is overcomplicating the solution. Adding unnecessary data structures or extra steps can make your code harder to debug and less efficient. Instead, focus on the core requirements of the problem, emphasizing clarity and simplicity in your implementation. A clean and straightforward solution not only reduces errors but also makes your thought process easier to understand, especially in interview settings. In interviews, it's important to highlight your understanding of the BST's properties. For example, demonstrate how in-order traversal takes advantage of the BST structure to provide sorted data in O, n, time. This shows that you can leverage the problem's constraints to optimize your approach. Additionally, be prepared to discuss trade-offs between recursive and iterative solutions. While recursion can be more intuitive, it often comes with higher space complexity due to the call stack. Iterative solutions, on the other hand, allow you to manage space more efficiently. When discussing your solution, emphasize when you've managed to avoid extra space, perhaps by modifying the tree in place or using constant space. Lastly, edge case awareness is critical. When explaining your approach, explicitly mention edge cases like empty trees or duplicates early on to demonstrate thorough and comprehensive thinking. For further practice, you can explore related problems such as LeetCode 230, kth smallest element in a BST, or LeetCode 98, validate binary search tree, which also leverage BST properties in different ways. Finally, let's look at some alternative approaches to solving this problem. One straightforward method is the brute force approach using a hash map. Here, you traverse the tree and record the frequency of each value in a hash map. Once you've collected all frequency data, you find the maximum frequency and extract the corresponding values. While this method is simple to implement, it requires extra space, which might not be ideal for large trees. A more space-efficient approach is to perform an in-order traversal while maintaining counters for the current value and tracking the mode. This method optimizes space usage to 1, but the implementation can be slightly more complex. For those looking to push the limits of efficiency, Morris traversal is an advanced technique that performs in-order traversal without recursion or an explicit stack, modifying the tree temporarily into a threaded binary tree. This method achieves additional space usage but is more intricate and prone to errors if not implemented carefully. Each of these methods has its trade-offs, so choose the one that best fits the constraints of your specific use case or interview scenario. Great job! To wrap up, we reviewed the key concepts, including frequency counting with hash maps and tree traversal techniques. Remember, mastering BST problems requires practice and attention to detail. Thanks for joining, and don't forget to like, share, and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!